in the last class we have talked about the material selection for a cantilever beam, and at that time our objective was to get a highly stiff but lightweight cantilever beam. Now in this class what we are planning to do is to see the same problem but in a different light. Now we are planning to select material for a similar cantilever beam with circular cross section, and it is loaded at its end, but now our objective is that this beam must have high strength and lightweight. So if you remember that in the previous lecture our cantilever beam problem had the material property index, which was actually square root of rho over square root of E. In fact, the performance index was square root of E over rho. So now let us see that for this new problem, in which we said that you have to have a high strength, not high stiffness, and lightweight, how this situation may change. So let us try to go to the board to explain this problem. So here we are again with a cantilever beam. Let us consider that the beam has a uniform cross section, and if I cut any section in the beam, then I will find out that it is circular in nature. Okay. So the cross section is circular in nature. Let us assume that this particular the diameter, let us say the diameter is D in this case, okay, and this circular beam has an end load F, okay, and our objective today is somewhat different from the last class. Now we are not bothered about the deflection, but we are bothered about the strength, that the cantilever should not fail. So our objective is that select lightweight but strong material system. That is the material system which has a high strength. High strength. Okay. So that is what is our objective, and keep in mind that in this case the free variable as usual is the beam diameter D. The length of the beam we cannot touch, that is of length L. And what is our constraint then? Beam length L, and let us say deflection. Of course, deflection would not come into picture in this particular case, but beam length and deflection delta. Now, in this case the beam should not fail. So that means I have to find out that what is the maximum stress that can generate in this beam due to the effect of this force F. Let us neglect, first of all, let us, for the simple engineering analysis, neglect self weight of the beam. So, with this condition, let us try to find out that what is the maximum stress that can come out in this particular beam. So, let us try to find that out using the basics of strength of materials. So, we try to use the basics of strength of materials. We try to find out that what is the stress in this case which is critical, as it is evident that the beam is undergoing bending. So, it is the bending stress which is critical, and that can be defined as at any point by the simple relationship that sigma equals to my over I, where m we will consider it to be the maximum bending moment, and y, that is perpendicular distance from the center, and I is the area moment. Okay. So, with this configuration and with this equation, let us call this to be our first equation, that sigma equals to my over I. I have to find out, of course, that what is the maximum bending moment that is possible in this beam. So, if I try to draw the bending moment diagram of the beam, now we know that maximum moment in this case will be coming at the fixed end, and it will become 0 at the other end, and the maximum bending moment here, the magnitude is FL. Of course, the deflection of the beam is downward. So, which means if I consider very close to this support, let us say BB, if I look at the BB, what is the state of stress, then I am going to see that this is the bending stress in which the maximum stress is. So, this is what is our the total distance, that is what is the diameter d, okay, and the maximum stress is going to happen at this particular point, okay, that is the sigma peak. So, sigma peak is going to happen maximum stress at the two extreme fibers at the two edges of the beam. Now, with that understanding, we can now write down all the numerical values, that m equals to FL in our case, okay, that is the maximum bending moment, y equals to d by 2, that is the farthest point, and of course, I equals to pi by 64 d to the power 4. So, as a result, if I use all these things using in equation 1, we get the new relationship as a function of d, that we get sigma equals to FL over pi by 64 d to the power 4 times d by 2, that is, it will come out to be 32 FL by pi dq, right. That is what is this stress versus the rest of the relationship. In other words, I can write that D equals to, I can write the equation here which will be useful for us further, that D equals to 32 FL over pi sigma, this is the sigma peak to the power 1/3. That is what is my equation 2, right. So, I get what is the maximum stress, and I can express the free variable D with respect to this maximum stress that will be coming to the system. Now, our objective is to also get a lightweight beam. Okay. So, we have to bring mass into the picture just like the last lecture. So, I am erasing equation 1 now, because equation 1 you have already understood and all these details related to it, and I am working on the mass of the system. Now, mass of the beam M equals to rho into pi by 4 d square into L, right. That is the mass of the beam. That is what is my third equation. So, I can use D from equation 2, that is the expression of D. So, if I use it here, then my M will be rho times pi by 4 times 32 FL by pi sigma peak times, we have pi by 4 d square. So, d is 1/3. So, this is 2/3 times L, right. That is what is the mass of the system. Now, let us try to divide this expression as usual like the last class into several segments and isolate that part which is related to the material property of the system. So, if I try to do that, then I will get the relationship as M equals to pi by 4 times 32 by pi, I can take it out, times 2/3. So, this is one part multiplied by, let us choose another color to write the other part, that is L to the power 2/3 and plus L. So, 5/3, and then I put another part using another color, let us say the functional part of the system into F to the power 2/3, that is the other part. And finally, we are finally boiling down to the materials part of the system, so that we can write it as multiplied by the rho over sigma p to the power 2/3. Okay. So, that is what we have. That means, if I try to write it down, this is the constant part, this is the geometry part, this is the function part or the loading part, and the last part this is the material property. Now you may tell me, what is this sigma p? How that can be the material property? Well, sigma p is the maximum stress that is coming to the system, and for many safe engineering design, we can at most take this sigma p, particularly if it is linear elastic systems, etc. Sigma p at most equals to sigma y, or in some cases if you keep a factor of safety, then you can write sigma p equals to sigma f by providing suitable factor of safety. So, whatever we say here, the performance index in this case is actually sigma y to the power 2/3 divided by rho. In other words, if you want to minimize this mass further and further, you must choose a material which has high strength and low density. Now, the relationship is not very simple that you just increase the strength 2 times and you get 2 times change in the reduction in the mass. No, there is a nonlinearity that exists here. So, it is 2/3 of the whole thing, and similarly with the density. So, that is where we need to once again draw this kind of a logarithmic curve, that suppose I say that the minimum constant value of this is constant value is c, then I can write that log of sigma y equals to 3/2 log of rho plus 3/2 log of c. In fact, if I try to visualize this graphically, so let us erase all these parts now because we have the material property here with us. But if I try to plot this log plot of sigma y versus log plot of rho, then we are talking about a line here whose slope theta will be approximately 56.3 degree, and of course the intercept is something that can be chosen. Okay, so you can choose it. Okay, so but the slope of the line, so what it means is that with certain values of c, you can either start from here or you can reduce the margin or you can increase the border. No matter whatever you do, that change will be here, but the slope of the line is going to be parallel, and that slope is determined by this relationship which says that that slope has to be 56.3 degree. Okay. So, let us look into the SB chart, that how this slope would look like. So, if I now go back to the SB chart, now if I go back to the SB chart, we can see that this is the strength versus the density plot, and we have many possibilities here. Let us look into once again the materials. In a low density side, we have materials like the foam group, which has very low density. So, this is the border case, 1 megagram per meter cube, that is what is the water density. So, all these materials are lighter than water. So, these materials are possible provided my line is below. So, if I draw any line corresponding to my minimum corresponding to my minimum's value of c, if my slope line goes like this, then some of these corks, some of the woods, flexible polymers, they come into picture. Otherwise they do not come into picture. If I consider the C value as something like 1 MPa or so, then they do not come into the picture in the current condition. And then what comes into picture? Gradually, if we go up, we start to see at the higher density side that we have some of the high performance polymers like PIC, polyether ether ketone, polyaniline, PMMA, this type of polymers will come. After that, we can see that the blue group, so that is from the yellow group we go to the plastic group. So this is so to say the foam group, and these are mostly the natural materials as it is shown here, and then we have the polymers here. Some of them are high performance polymers. We get elastomers also, but elastomers also may fall below the line depending on our choice of the minimum intercept. And then above that, what are we getting? We are getting CFRPs, GFRPs, etc. This is what we are getting. Beyond that, we are actually getting the ceramics, and even beyond that we are getting things like titanium alloys, steels and some of the metals. But if you see, if I go that far away, I may get a high value of the strength, but I am also going to get a high value of the density value rho. So for example, suppose I go to steel, for example. So for the steel, something like, can go up to something like 1400, let us say MPa, 1400 MPa, that is the sigma y, say, for the steel approximately. Okay. So and on the other hand, the density is approximately 7.8, right, megagram per meter cube. So basically we can then use this relationship that this is 1400 to the power 2/3 divided by 7.8, and you can see that what is the value that you are getting out of it. And similarly you can calculate this for some of the other cases like PMMAs. Okay. So this is for steel, this is for steel, you can check it. And for PMMA, if you do the same thing, it will be something like, let us look at PMMA, it is like the maximum value if we take for PMMA somewhere like 10, 20, 30, 40. So 40 2/3, and if you look at the density wise, it is less than water, so it is 2, 3, 4, 5, 6, so about something like 0.6. What is the value coming? Just check it and see that whether PMMA gives you a higher performance index than the steel. That's the way we choose, and finally based on a particular application we consider whether we consider a very high value of rho or not. You may actually have some kind of a cutoff value of the density, and accordingly we select a particular material. This is where I will close in this particular lecture, and in the next lecture we will choose another case which is not just a single objective, but it has multiple constraints. Thank you.